Welcome back to This Week in Geology, and today we'll be going into glacial ice, Perseverance again. We'll be looking into Pyrite, and then we'll also be digging into some glacial ice articles as well. So let's just jump right into the article. So the first article is from Smithsonian Magazine, and it's the Perseverance rover shares its first video and audio of Mars. The Curiosity rover landed the same way in 2012, but the engineers who designed the system hadn't seen it in action until now. NASA released the audio on Monday afternoon, alongside stunning footage of the landing recorded by several cameras mounted to the rover and sky crane. Kenneth Chang reports for the New York Times. It is the first conventional video recorded on Mars, distinct from the animations that have been created by flipping through a series of photographs. Engineers at NASA's Jet Propulsion Laboratory will use the video to analyze the landing system, but it also has a broader purpose to give anyone who sees it a glimpse of a glimpse of what it would be like to land on Mars. Okay, that wording was a little bit weird, but it makes sense. So let's jump into this video. Oh wow.
Navigation has confirmed that the parachute has deployed, and we are seeing significant deceleration.
Heat shield set.
Perseverance is now slowed to subsonic speeds, and the heat shield has been separated.
Originally it was 430, now it's jumped down to in the hundreds of kilometers per second. That's pretty intense. That is really cool. Look at those dunes. There's a bunch of dunes. There's a dune field. I didn't realize that. It feels like I'm watching a sci-fi movie right now. This is intense.
Touchdown confirmed. Perseverance safely on the surface of Mars.
Yeah,
Ready to begin
nice.
digging the sands of top life.
That's awesome. Wow, that is intense. It felt like I was watching a sci-fi movie. So the video begins from the perspective of a camera at the top of the aeroshell, which is the capsule that holds the rover. The red and white parachute, the most massive parachute deployed on Mars, shoots back and opens. You can get a sense really of how violent that parachute deploy and infiltration are. The parachute is packed so densely that the pack is basically the same density as oak, and it's about 150 pounds. It gets launched out of the spacecraft with a mortar, which is basically a cannon, with a muzzle velocity of around 100 miles per hour. When the landing capsule reaches about 7.5 miles above the surface of Mars, the heat shield drops out from below another camera. The footage shows it shrink as it falls down into the rocky Mars terrain. Soon after, the landing system begins to use terrain relative navigation to find a safe spot to land. A map of hazards in the Jezero crater landing zone show how high the stakes were for Perseverance, as it's speckled and striped in red danger zones. And I'm guessing that means terraneous areas, the red areas. And they're looking to land in the blue. So if they land on a red area, that's no bueno. When the capsule comes within 1,000 feet of touchdown, the ground-facing camera shows wind buffeting the sandy surface of Mars, and the sky crane maneuver begins. Two cameras, one pointing up from the rover and one pointing down from inside of the sky crane, show the moment that Perseverance drops out of the crane like a cat burglar. The rover used pyrotechnically fired blades to sever the cord and touch down on the Martian surface. It gives me goosebumps every time. Yeah, I got goosebumps watching them celebrate and watching that happen. That was really cool. That was a really intense video of watching them, parachute down with multiple different rovers. Dominantly Perseverance. It was like watching a sci-fi flick. It really was. All right, so our next article is about asteroid dust found in a crater closes the case of dinosaur extinction. And this one's from the University of Texas at Austin. Researchers believe they have closed the case of what killed the dinosaurs, definitively linking their extinction with an asteroid that slammed into Earth 66 million years ago by finding a key piece of evidence, asteroid dust inside the impact crater. Death by asteroid rather than by a series of volcanic eruptions or some other global calamity has been the leading hypothesis since the 1980s, when scientists found asteroid dust in the geologic layer that marks the extinction of the dinosaurs, the KT boundary. And I'll have a picture of that pop up. The discovery painted an apocalyptic picture of dust from the vaporized asteroid and rocks from impact circling the planet, blocking out the sun and bringing about mass death through a dark, sustained global winter, all before drifting back to Earth to form the layer enriched in asteroid material that's visible today. In the 1990s, the collection was strengthened with the discovery of a 125-mile wide, and I honestly can't even say that word, Chicxulub Chicxulub impact crater beneath the Gulf of Mexico that is the same age as the rock layer. The new study seals the deal, researchers said, by finding asteroid dust with a matching chemical fingerprint within that crater at the precise geological location that marks the time of the extinction. The telltale sign of asteroid dust is the element iridium, which is rare in the Earth's crust but present at the elevated levels in certain types of asteroids. An iridium spike in the geologic layer found all over the world is how the asteroid hypothesis was born. In the new study, researchers found a similar spike in a section of rock pulled from the crater. In the crater, the sediment layer deposited in the days to years after the strike is so thick that the scientists were able to precisely date the dust to a mere 2 decades after impact. The dust is all that remains of the 7-mile wide asteroid that slammed into the planet millions of years ago, approximately 65 million years ago, triggering the extinction of 75% of life on Earth, including all non-avian dinosaurs. Birds were able to survive through this. And researchers estimate that the dust kicked up by the impact circulated in the atmosphere for no more than a couple decades, which helps time how long extinction took. If you're actually going to put a clock on extinction 66 million years ago, you could easily make an argument that it all happened within a couple decades, which is basically how long it takes for everything to starve to death. It just further proves that, you know, an asteroid definitely aided causing the dinosaurs' extinction. I know that volcanism was, I forget if it was the Siberian traps or the Deakin traps. I'll have that pop up on the as I edit this, but it was the volcanism teamed with, you know, the asteroid, the effects of the asteroid impact on the planet that definitely helped aid the extinction of the dinosaurs and many other animals that lived during that time. Birds were able to survive, as did mammals, which allowed mammals to take over in the Cenozoic. Next article is missing ice problem finally solved. This one, and this is my favorite scientist of all time, Alfred Wegener Institute, Helmholtz Center for Polar and Marine Research. So during glacial periods, the sea levels falls because vast quantities of water are stored in the massive inland glaciers. To date, however, computer models have been unable to reconcile sea level height with the thickness of the glaciers. So during transitions from glacials to interglacials, the glaciers on Greenland and in North America and Europe wax and wane over tens of thousands of years. The more water that is stored in the mighty glaciers, the less there is in the oceans, and the lower the sea level is. Climate researchers are now investigating to what extent the glaciers could melt in the coming centuries due to anthropogenic climate change and how much the sea level would rise as a result. To do so, they're looking back into the past. If they can understand the ice growth and melting during past glacials and interglacials, they'll be able to draw valuable conclusions about the future. Sediment analysis versus global climate modeling. The missing ice problem is based on the one hand on an analysis of sediments from core samples collected from the seafloor in the tropics. These contain traces of corals that can still tell us today to what extent the sea level rose or fell over the millennia. Why? Because corals only live in well-lit waters near the ocean surface. Sediment cores indicate that 20,000 years ago, the sea level in the tropics implied that the sea level is roughly 130 meters lower than it is today. On the other hand, previous models have suggested that glacial masses weren't large enough 20,000 years ago to explain such a low sea level. To be more precise, for the sea level to be that low on a global scale, an additional volume of water with twice the mass of the Greenland ice sheet would have had to be frozen, hence the missing ice problem. So using geochemistry to determine 20,000 years ago, basically the discrepancies between what we can prove in terms of the glacial thickness and then the levels of the ocean at certain areas, such as in the tropics. They found that corals in the tropics showed that the sea level was actually much lower, about 130 meters. That's a significant difference from what was expected, you know. So the next article is also about glacial ice. This one is the melting of large icebergs is a key stage in the evolution of ice ages. So a new study in which the Andalusian Earth Sciences Institute participated has described for the first time a key stage in the beginning of the Great Glaciations and indicates that it can happen to our planet in the future. The study claims to have found a new connection that could explain the beginning of the ice ages on Earth. The study claims to have found a new connection that could explain the beginning of the ice ages on Earth. The Antarctic iceberg melt could hold the key to the activation of a series of mechanisms that cause the Earth to suffer prolonged periods of global cooling. It has long been known that changes in the Earth's orbit as it moves around the sun trigger the beginning or end of a glacial period by affecting the amount of solar radiation that reaches the planet's surface. However, until now, the question of how small variations in the solar energy that reaches us can lead to such dramatic shifts in the planet's climate has remained a mystery. In this new study, a multinational group of researchers proposes that when the Earth's orbit around the sun is just right, the Antarctic icebergs begin to melt further and further away from the continent, moving huge volumes of fresh water from the Antarctic Ocean into the Atlantic. This process causes the Antarctic Ocean to become increasingly salty, while the Atlantic Ocean becomes fresher, affecting overall oceanic circulation patterns, drawing CO2 from the atmosphere and reducing the so-called greenhouse effect. These are the initial stages that mark the beginning of an ice age on the planet. Within this study, the scientists used several techniques to reconstruct oceanic conditions in the past, including by identifying tiny fragments of rock that had broken away from Antarctic icebergs as they melted into the ocean. These deposits were obtained from marine sediment cores recovered by the International Ocean Discovery Program during Expedition 361 off the sea margins of South Africa. These sediment cores enabled the scientists to reconstruct the history of the icebergs that reached these latitudes in the last 1.5 million years, this being one of the most continuous records known. So the final article of this episode, I picked this one because pyrite has always been my favorite, just based on the fact that it crystallizes in perfect cubes, and I'll have a picture pop up of what it looks like when it's allowed to grow in open space. Pyrite is fool's gold. So when using pyrite to understand Earth's ocean and atmosphere, think local, not global. So scientists have long used information from sediments at the bottom of the ocean to reconstruct the conditions in oceans of the past, but a study raises concerns about the common use of pyrite sulfur isotopes to reconstruct Earth's evolving oxidation state. These signals aren't the global fingerprint of oxygen in the atmosphere, according to new research from Washington University in St. Louis. So the ocean floor is vast and varied, making up more than 70% of the Earth's surface. Scientists have long used information from sediments at the bottom of the ocean, layers of rock and microbial muck, to reconstruct the conditions in oceans of the past. These reconstructions are important for understanding how and when oxygen became available in Earth's atmosphere and ultimately increased to the levels that support life as we know it today. Yet reconstructions that rely on signals from sedimentary rocks but ignore the impact of local sedimentary processes do so at their own peril. Their new study, published February 26 in Science Advances, is based on analysis of a mineral called pyrite, or iron sulfide, that is formed in the presence of bacteria. When it's chemical reduced iron and sulfur, the burial of pyrite in marine sediments is one of the key controls on oxygen levels in Earth's atmosphere and oceans. The researchers compared pyrite and sediments collected in a borehole drilled in the shelf just off the eastern coast of New Zealand with sediments drilled from the same ocean basin, but hundreds of kilometers out into the Pacific. A postdoctoral fellow at the Weizmann Institute first questioned the way that pyrite has been used as a proxy in a study published in PNAS in in 2017 using Mediterranean sea sediments. Yeah, you guys should probably change that acronym. Once you go below that water depth, sulfur isotopes apparently are not sensitive to things like climate and environmental conditions in the surface environment. The Earth is a complicated place, and we need to remember that when we try to reconstruct how it has changed in the past, there are a number of different processes that impact the kinds of signals that get preserved. As we try to understand Earth's long-term evolution, we need to have a more nuanced view of how to extract information from those signals. So an interesting article, they're saying that local sedimentation, especially in shallow areas, they have a shallow and a deep borehole, and they took over 100, almost 200 samples from these two boreholes off of the east coast of New Zealand, and basically they studied those isotopes, and they realized that in the shallow borehole in the shallower zone, it was more locally controlled, whereas the changes in environmental conditions or sedimentation, those would affect the shallow, whereas the one in the deeper zone, the deeper borehole, discovered more information about the global currents, the oceanic currents that change and shift as climates change. It's a very interesting article, and it's going to be interesting to read this as they learn more about this particular topic. And that'll be it for this week in geology. I appreciate you guys watching. Later, Essentials.